There are two different formulas for angular momentum. One of them involves shape via rotational inertia and spin via angular velocity. You find the vector angular momentum by examining what it is that's spinning and how fast it's spinning. This is most useful if you have one object of a known shape that is spinning at a known rate. We'd call this revolving. Pool balls spin, dancers spin, electrons spin. The Earth spins about its axis, the Moon spins about its axis. All these are one single shape spinning around one axis of rotation. We haven't introduced the idea of an orbit, or of circular motion in general, or of something that's not tumbling head over heels, but is just moving in a circle, as per these two hamsters whose owner, in a moment of video cuteness, has decided to put them on an LP exactly as all the problems in first-year physics textbooks say, but have forgotten to put the hamsters facing the right way. They're reasonably patient hamsters, and I have no idea what the moment of inertia of a hamster is. I'm not going to look it up, and I am not using calculus to calculate that thing. We're going to treat this hamster as one single unitary hamster sphere of constant density. Why? Because there it is. It's right here, and I can follow it. And look, there's the other one. Each one is orbiting at a certain location. There's the inner hamster and the outer hamster at a known radius. And if we use enough frame analysis, we can find the number of centimeters per second or meters per second, the speed and the momentum with which each hamster is traveling. This formulation, based on location and momentum, that is to say location, mass, and speed, is much more helpful if you have several objects in a system moving in a circular path. If you have orbits, if you have laps, if you have anything that goes round and round. Let's take a look at a couple of examples. Stars spin. Galaxies spin. It's what they do. It's how they're born. We'll see in the next chapter how this is an integral part of the life cycle of a star. So we've got one galaxy of a known shape, spinning and spinning. Gravity draws the stars closer and closer and closer together. It draws the stellar core closer and closer and closer together. And we know from basic conservation of angular momentum that if you take mass that's outside the system and move it in toward the center, we're expecting the galaxy to spin faster. Let's see how this works mathematically. Although galaxies are in the shape of disks or spirals, let's zoom in on the dense core at the center and assume that that core is, when you get down to it, basically spherical. We're going to take a look at a spherical core, mass m, radius r, and contracts to half its size. When this happens as part of the death cycle of the star, what does this do to the rate at which it spins? Use your new formula and set up the conservation of angular momentum before and after. Solve for the new omega, the new rate at which it spins, as compared to the old one. Pause to do your work and then press play to check it or to get yourself unstuck. Ready? Before, you have a certain angular momentum. Afterward, you have the same angular momentum. Unless somebody comes with a screwdriver and starts banging on the galactic center, I don't think an outside force is due to interfere, so we can say that they're equal. Look up the moment of inertia of a sphere. Press play when you're stuck again and need to check your work. Looked it up? 2/5 m r squared? There it is, 2/5 m r squared, or 2/5 m nu r squared. Watch those parentheses. If you got the wrong answer or you didn't use parentheses, you're going to get the wrong answer. Put those parentheses in and fix your work. Square it. See what cancels and what's left. Press play to check your work when you're done. Ready? Canceled out the m's, cancel out the r's, cancel out the 2/5. What's left? Got 1/4 on the right-hand side. Omega 1 is 1/4 of omega 2. Now, we were solving for omega 2, the new rate of spinning. Multiply both sides by 4. You'll get omega 2, the new rate of spinning, is 4 times the old rate of spinning. If you take a sphere and contract it so that its radius diminishes by a factor of 2. If its radius, not its volume, not its area, but its radius, is half as big as it was before, that's going to have the effect of making that core spin 4 times faster. And hey, if the spinning was what was causing it to contract to begin with, now it's contracted half as much. It spins 4 times faster. 4 squared is 16. That means it's going to contract 16 times as much. If it's got 1/4 of the radius, that means we are going to have a snowball effect. That this is going to go out of control. It's going to spin faster, so it's going to contract, and it's going to contract until it spins faster. If this is part of the birth of a star, this will happen until the interior temperature reaches 7 million Kelvin and the star ignites. If this is part of the end of a star, we are going to get pressures and temperatures high enough for protons and electrons to fuse into neutrons. We are going to get a neutron star with the accompanying side effect of a tremendous explosion we call a supernova. Now, R cross P. Usually we're using this for something that, like this doggy, is not somersaulting head over heels or spinning round and round itself, chasing its tail. This dog is simply going for a run. So happens that the dog at the playground is having a grand old time going for a circular run on a circular object. Presumably the merry-go-round was at rest before the dog jumped on, and it's still going to have a total angular momentum of 0. So when the dog runs clockwise, the carousel is going to spin counterclockwise. How fast? Well, the total angular momentum is equal to 0. So if we can find the dog's angular momentum, then the angular momentum that the carousel receives is going to be equal and opposite. Mass of the dog will need for the momentum. Velocity of the dog will need for the momentum. If we can time these frames and figure out how massive the dog is, how fast it's running, and last but not least, what's the radius in between the center and where the dog is running? Not the whole carousel, just where the dog is running. What's that radial distance? We'll be able to do R cross P, find that angular momentum, and say that the carousel is going to have an equal and opposite angular momentum. Note that vector direction. Just like we said in class, this is right-hand rule. The dog is moving clockwise in a circle. Curl your fingers around the location. Make sure you get a nice right angle here. Right-hand rule says the angular momentum is going to be vector downward. Let's do a numeric example for which we have access to masses and speeds, or at least can get them from a telescope. This kind of motion is very common in a binary star system. You've got 2 stars orbiting about each other, that is, orbiting about their common center of mass. 2 stars mass m, we have found speed v from the frequency of the light emissions, and we know that they're a distance d apart. If gravity moves them in closer to each other, as gravity is known to do, how will this change their orbit speed? What do you think? Faster? Slower? If you said faster, you're right, and we're using our old I omega. Move the mass in closer to the axis of rotation. We're going to have a different moment of inertia. Specifically, our moment of inertia is going to go down because our mass is closer in, and then the rate at which we're rotating is going to go up. We want to know how this is going to change the speed at which these stars are moving in space. Check. We're given the distance between them. The distance to the axis of rotation, that is r, the radial distance, is half that. D is the diameter of that circle, see? Also check. We need the momentum of each star. Well, we're given m and we're given v, so that's not so bad. Last check, please note that this is a system of 2 objects. There are 2 stars in the system. So, set up your before and after. Find the total angular momentum in the system, transfer it over to your after column, and knowing that the stars are now 2/3 d apart instead of just d apart, find the new linear velocity of each star. Pause, solve, press play to get unstuck, or check your work. Ready? Well, we got one star, r at half d, and a momentum of mv. All of that angular momentum is definitely going to be in the downward direction. R and p are at right angles to each other. We are good to go with the cross product. L2. It's an identical star. Not all binary star systems are two identical stars. Plenty of times they're going to have a different mass. This one, they have the same mass. Atom. MVD, still all in the downwards direction. I'm going to be a little bit sloppy about direction in this example because we know everything is in the downwards direction. Move the total. We've got MVD of angular momentum that needs to be shared between count them, two stars, L1 and L2. Who are we kidding? L1 and L2 have the same mass. They have the same distance from the center. We're going to have one new angular momentum for each star, and that is just going to be half of our new MVD. However, our R is different. It's 2/3 d from star to star. That means it's 1/3 d from star to center. That means each star has the old mass, the new velocity, and a radial distance of 1/3 d. You can do 1/3 d mv, or you can do 1/3 mvd plus another 1/3 mvd. Either way, you're going to get 2/3 mvd on this side. M's cancel out. V's. Ooh, these do not cancel out. How about that? D's definitely cancel out. Finish your algebra. Play to check your work. Old velocity is 2/3 of the new velocity. If you've gotten that far, now notice we're solving for the new velocity. Multiply the 3, divide by 2. You're going to get your new velocity is 3/2 of your old velocity. That is, your new velocity is 1.5 times your old velocity. And there's your answer. How fast will the binary stars spin? If they move in by that distance, they'll spin 1.5 times as fast, or 50% faster. If this keeps on continuing, if they continue moving closer and closer and closer and closer together, you're going to have the two stars collide and fuse into one in the kind of event that LIGO observed in the fall of 2015, almost as soon as it turned on. Two enormously massive stellar bodies, actually they were so big they were black holes rather than stars, colliding in space, sending ripples of gravitational waves outward through the universe.